Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alright guys, so in this video, I will talk about topic of magnetic torque on a current carrying conductor. Alright, so before we go to the topic, the concept for the magnetic torque, so let's see on the fundamental of the torque itself first. So let's consider, so we have one disc, okay, so we have one disc here, and the disc is placed in XY plane. So we have x-axis here and we have y-axis here. Okay, because of we have this setup, so we will have the center of the disc is placed on the origin, and at the same time, so we will have our z-axis is pointing outward from our paper in the center of the disc. So the disc have some radius r here. So instead of by represent the distance between center to the edge, so by using the radius, so we are using another vector, so we call it as a vector of d. So this is vector of d. So the vector of d is represent the direction and distance between our center of the disc and the edge of the disc. So let's say we put or we apply some force on this point, okay, and the force is pointing downward as shown in this figure. So because of we are applying some force in a downward direction, so instead of by making this the disc is moving downward, okay, because of we have pivot axis here, so instead of moving downward, so the disc will be rotated. All right, and the direction of the rotation for the disc is in a counterclockwise. So by considering the direction of the force applied on the edge of the disc. All right. Generally, so the torque can be expressed by using this expression. So whereas this is the vector of torque is equal to vector of d cross with the vector of force or Fm. So in this case, the vector of d also known as the moment arm, okay, moment arm vector. So generally, so by considering this motion, so basically the torque will be produced in the z-axis. All right, so when the disc start moving, okay, and then we fix the point of the force produced at the fixed point on the edge of this cylinder, so we see that the point of the force applied will be moved, okay, around this edge according to the position of the motion. So we see that the direction of force will be somehow changed, okay, according to the direction of the tangent of this edge of the disc, and it will make some angle, so between the force vector and the moment arm vector with the factor of theta. All right, so because of that fact, so basically we will have amplitude of this mathematical operation will be function of theta. If we consider the magnitude of the arm vector is equal to radius of this cylinder, all right, so it's equal to r, and the magnitude for this force is equal to F. So therefore the general solution for this expression can be rewrite as this one. So we have t, so the vector of the torque is equal to z cap. Z cap is the direction of the torque produced based on this case. R dot with F dot with sine theta, and then the unit of it is a Newton meter. Alright, so basically the torque will be produced in the z cap direction. Alright, so depending on the direction of the rotation. So let's say in this case, so we are having a direction of rotation in a counterclockwise. So therefore, the torque will be produced in the z cap direction. If we reverse the direction of the rotation to the clockwise direction, so basically the torque will be produced in the minus z cap direction. So this direction of the torque produced will be comply with the right hand grasp rule. Alright, so we have a right hand grasp rule, so as shown in this like this. So the thumb will be referred to the direction of the torque produced, and our forefinger will be refer to the direction of the this motion. So for example, in this case, so we have the direction of the rotation in a counterclockwise. So we have like this, right? So counterclockwise, and the thumb will be pointing upward, which is represent the direction of the force. And by considering this plane, so the direction of the force produced will be in a z cap direction. So if we reverse the direction of rotation to the clockwise, okay, like this one, so we will have the direction of the rotation now is in clockwise direction. So our thumb will be pointing downward, all right? And that pointing, that thumb pointing will be same as the negative z cap direction in this particular setup. All right, so at the same time, basically, when we want to discuss the magnetic torque. So basically, the magnetic torque is the torque that produced on the conducting loop, so under influence of magnetic force. All right, so in order to understand this topic, so let's see this figure. Okay. All right. So let's say we have one singleton loop here. Okay, in this shape of rectangular. So the length of this loop is equal to B, and the width of this loop is equal to A. And then we place the center of this loop at the origin of the xy plane. All right, so we have x direction and y direction here. The center of it is the center of the rectangular loop, and at the same time, so we will create one, what we call it as a pivot axis on y axis. Okay, so we supply this loop with some value of the current in this direction. So the direction of the current is somehow in a counterclockwise direction. All right, and we can divide this rectangular shape of loop into 4 different segments. Okay, so we have first segment here, the second segment here, third segment here, and the fourth segment here. All right. At the same time, so in order to create magnetic force on this particular loop, all right, so we place this loop inside a magnetic field, and the direction of the magnetic field is as shown in this figure. Okay, so in direction of x cap or x-axis. So if we look in this loop into this view, okay, so we will have the view is similar like this one. So we have, this is represent our loop arm 1, so which is the loop from the first segment. So because of the direction of the current is pointing downward, so by considering this view in this side, okay, so we will see that the direction of the current here will be flowing outside from our paper plane. Okay, so because of that, in this particular case, so we are using the dot symbol here. So in this part, so we have loop arm 3, which is the third segment of the conducting loop. So because of the current of this segment is flowing upward, okay, by referring to the setup. So by considering this view, so we will see that the direction of the current here will be flowing inside our plane. So that's why we will represent the direction of the current by using X symbol. So we still have our pivot axis here is equal to 0. So similar like what we having in this setup. And the direction between our axis and the arm, okay, loop arm 1 and loop 1, 2 will be represented by the other vector. Okay, so in this case, so we are representing it by using d vector or moment arm vector. So the vector d1 is represent the direction and distance between our pivot axis to the loop 1, and the d3 vector of d3 will be represent the distance and direction between our pivot axis to our loop arm 3. And the magnitude of this vector is equal to half A, okay, which is we have the width of this loop is equal to A, and our pivot axis is located to the center of this length. So that's why we will have the magnitude for this vector is equal to half of A. Alright, so for now, let's neglect first in terms of the direction of the force produced and the direction of the counterclockwise. So we do some the calculation first, then we will see how can we determine the direction of the force and the direction for the rotation direction. Alright. As I explained just now, so basically we can divide the loop into 4 different segments. So because of that, so we will derive the force expression for each segment. So by referring to their segment. Alright, so we will have the general expression for the magnetic flux density is given by this expression. So we have vector of B is equal to x cap. So this is the direction for the our magnetic field here. So in x direction, multiplied by the B naught. This is amplitude that represent our magnetic flux density, and the unit of it is a Tesla. So this is our general expression for the torque. So that means that in order to calculate the torque produced on this particular loop, so we need to derive the vector of D and the vector of F magnetic force 2, okay, that act on each segment. Alright, so let's see for the first segment first. Right, so we will have general expression for the force or the magnetic force is equal to F is equal to I line integration of dl. So dl is the vector that represent the distance, that represent the direction for the current, okay, at the same direction of the current, cross with the vector of B. So B is our magnetic flux density. So the general solution for this particular equation is equal to this equation, which is I vector of L cross with the vector of B. Okay, the unit of it is Newton. Alright, so in order to determine the vector of L, so let's see for this first segment. So the current is travel from this point until this point, and this will be our represent our vector of L. So because of the direction of the current motion in a minus y cap direction, and the amplitude for this length, okay, the amplitude for this length is equal to B. So that's why we will have our general expression for the vector of L is equal to minus y cap multiplied by the B. So if we replace this equation with all the parameter that we know, then we will have F1 is equal to I minus y cap B cross with the x cap B naught. And by solving this expression, so we will have the expression for the force that act on the first segment is equal to Z cap I B multiplied by B naught. Alright, so on the second segment, so in this segment, so we will see that in this case, our vector of L is in x cap direction, in a reverse, in a negative x cap direction. And the amplitude of it is equal to the width of this loop is equal to A. So that's why we will have the vector of L is equal to minus x cap multiplied by A. And by put all the parameter that we know inside this expression, then we will have our F2 is equal to I minus x cap A cross with x cap B naught. So by considering this operation, so x cap cross with x cap will be result 0. So therefore on this particular segment, so the force applied to it is equal to 0 Newton. Alright, so in the third segment, so in this segment, so we will have almost similar condition what will happen in the first segment, okay, except the direction of the current is different. So in this case, the direction of the current in a positive y direction. So therefore, the vector of L is equal to y cap multiplied by B, okay, so which is the distance or the length of this loop. So by solving this expression, okay, by considering all the parameter that we know, then we will have our value for F3 is equal to minus Z cap IB multiplied by the B naught. Alright. So now let's look on the last segment, okay, which is for the segment number 4. Alright. So this segment. So similar like what we have in a segment 2. Okay, so we have direction of the current in positive x cap. So the L vector, okay, because of that the L vector will be in the x cap direction, and the magnitude for L cap is equal to A, right? And because of the direction of the current and the direction for the magnetic flux density in the same direction, so therefore the total force act on this segment is equal to 0 Newton. All right, so based on what we have been derived just now, so we have seen that the force that act on the first and the third segment, so we will have the same amplitude. All right, so we have on the first segment is equal to z cap IB B naught, and the third segment is equal to minus z cap IB B naught. So the amplitude is the same, but the direction it will be different. All right, so the first segment, the direction of the force will be pointing up to the positive z, okay, and the third segment will be pointing to the negative z. Right, but the same with the same amplitude. So however, for the second and fourth segment, okay, so because of we have direction of the magnetic flux density, the vector for the B and the vector of L are the same in the same direction, so we will see that so the force on the second and the fourth segment will become 0. So because of that, in order to find how many total of the torque produced in this particular case, so we can neglect, okay, the force that produced on the second and the fourth segment. All right, so basically the torque produced will be the summation of multiplication or the cross product between the vector of D and Fm of each segment. All right, so because of the fact that the segment or the force on the segment 2 and 4 will become 0, so in this case, so we will only consider the force that produced on the first and the third segment only. So because of that, so we will have the T, the vector of T, right? So represent the torque is equal to vector of D, okay, moment arm for the first segment. So cross with the F1, so which is the force produced on the first segment. So plus with the vector of D3, so basically the moment arm on the third segment cross with the F3, which is the force that produced on the third segment. All right, with the rest will become the 0, especially in terms of on what happened in our second and the fourth segment. So by referring or by replacing with all that parameter that we know, for example, for the vector of D1 is equal to minus x cap. So we have here one here. So the direction of this vector in minus x cap direction. So we have minus x cap, and the amplitude of it is equal to half of the width. So we have half of A. So cross with the z cap IB B naught. So this is the force that produced on the first segment. So plus with x cap half of A. So this is the vector of D3. So direction will be in a direction of it is in a positive x direction. So x cap, and the amplitude is equal to half of A. Right? So we have half of A here, and cross with minus IB B naught. So this is the direction of the force produced on our third segment here. So by solving this expression, so we will have the torque will be produced in a y direction, okay, for both expression. And if we add it together, then we will have the total torque is equal to y cap AB, all right, AB. So the width multiplied by the length of this loop. So I, so the value of the current injected inside this loop, and multiplied by the B naught. See, this is the amplitude for this particular magnetic flux density. And by considering this operation will be result area of the loop, so we will have y cap is equal to A. So this is area of loop multiplied by the value of the current, and as well as the magnitude for the magnetic flux density. All right. The torque equation that we have been derived just now, okay, so in this case is only valid if the the direction for the magnetic flux density vector is parallel with the plane of the loop. Alright, so if we look back into our figure, so this is our direction for the magnetic flux density, and this is our plane. Alright, so whereas the direction of this vector and the plane is parallel. So basically what will happen if we have this kind of force acting on the each segment of the loop. Alright, so as we have been derived just now, so the F1 will be act on the Z direction, okay, so Z cap direction, and our F3, which is the force that act on the loop arm 3, will be produced in the direction of negative Z cap. So what will happen if we have this kind of condition? Okay, so because we have a pivot axis here, so this loop will be start rotating. So when this loop is start rotating, so we will have basically the direction for the magnetic flux density will not parallel with the plane of the loop. Alright, so this condition is explained so by this figure. Alright, basically when this loop start begin to rotate, okay, so basically the torque will be decreased until our B or vector B, so magnetic vector for magnetic flux density, is perpendicular with the plane of the loop. Okay, so this is our original position for the loop. Alright, so when we rotate the loop, so until a certain position, so in this particular position, so we will see that our B is perpendicular with our loop. So in this particular case, the value of the torque produced will become 0. So we will see as well the magnitude for the moment vector will be changed. Okay, so from half to or A per 2 until is equal to A per 2 with the factor of sine theta. So whereas this theta is represent the angle between the moment here and the force produced. And because of that, so basically the magnitude for the torque will be changed in terms of sine theta. So from the equation that we derived just now, so basically the torque, the magnitude of torque is equal to A, okay, area for the loop multiplied by I, so current inject inside the loop, and the amplitude or the magnitude for the magnetic flux, then it will change into IA B naught. So I is still a current inside the loop, A is the area for the loop, and this is our magnitude for the magnetic flux density. And we add another factor, which is the sine theta, okay, which is represent the angle between our moment arm vector and the force that supplied in this particular arm. And so we will see that, so basically the torque is depend on the angle between D, vector D, so which is our moment arm, and as well as our force. So, and basically if the loop is made from more than one turn, okay, so let's say with the number of certain n number of turn, so basically the torque can be calculated by adding a factor of the turn. Okay, so in this case the magnitude of the torque is equal to n, the number of turn, multiplied by I, so the current that injected inside this loop. Alright, so multiplied by A, the area for the for that particular loop, and the B naught is the magnitude for the magnetic flux density, and the sine theta. Okay, basically the angle between moment the vector of D and the vector of F. So in this case, so the expression for NIA, so turn, current, and area of loop, is depend as the magnetic moment. So the magnetic moment is another vector that represent, okay, for example, we have this is our loop lane. Alright, so the magnetic moment vector is the vector that exists perpendicular, okay, to this loop plane. Okay, so we call it as a vector of M, and this vector of M have unit vector of equal to n cap. Alright, so therefore in a vector form, so basically our magnetic moment can be represented by this expression. So we have the vector of m is equal to n cap, so unit vector for this particular vector NIA, so number of turn, current, and as well as the area for the loop, and the unit for this vector is equal to ampere meter squared. And then from this expression, so we can have another general expression for the vector of t is equal to vector of m across with the vector of b, and the unit is still the same for the torque, is Newton meter. Alright, so in order to express your understanding, alright, towards what we have been done in this topic, so by referring to this figure, okay, if the A is equal to 10 cm, so B is equal to 30 cm, so current injected inside the loop is equal to 10 ampere, so number of turn for this loop is equal to 10, and B is expressed as this one, so x cap 2 millitesla. Alright, so you need to plot the torque versus angle of rotation of the loop. Alright, so first you need to calculate, so what is the torque expression, okay, so during this initial position, and then after that, so we need to add the factor for sine theta, okay, which is represent the angle between our moment arm vector, so d vector, and the vector for the f. So and then for this expression, so please plot the torque versus angle of rotation. So angle of rotation is different compared to this angle, okay, so the angle of the rotation is depend on the position of this loop. So for example, during initial, so this is 0 degree. Alright, so when we move at certain degree, for example here, so let's say this is phi, so this is referring to the angle of rotation. Alright, so as usual, so please use your handwriting, so provide your name and matrix number, okay, in your answer. So scan and submit it to the link that provided. Alright, so that's all. Should you have any question, so please do not hesitate to submit it. Alright, so that's all. Thank you, and good luck.